Okay, I want to show you how to design a pipe using ECcalc27, an Excel spreadsheet. In this spreadsheet, it has 4 sheets to it. If you look at the bottom left, you see the tabs for each one. You click on the tab and you go to the sheet. All 4 sheets have different colored cells, and these light blue ones here are where you input information. You enter information, and they're usually headed by dark blue. If you notice right here on sheet 1, the pipe design steps are listed for you, and this is a very condensed version of what I've listed on my website, and this video is just a supplement to what I've listed on the website because every little detail is right here. So be sure to go to this direction to get all the complete information on designing. As you can see, it's long, but compared to some of the other more complex programs, this is simple. Trust me, this is easy. So basically, let's just go through the process here. On sheet 4, you need to enter in the exhaust port widths, which is explained on my website right here. In this case, it'd be this width plus this width plus this width every millimeter down. If you stick a piece of paper in your cylinder and press along the edges of the ports, that will impress the dimensions of the ports on the paper, which you can outline with an ink pen, and then with a ruler mark on each side 1 millimeter, marking every millimeter going down, and then draw a line through each one, and then with a ruler measure the middle distance along each space, 1 millimeter space, and then when there's more than one, you add those together and just write them down, and that's what you're going to be using right here. The widths of the total exhaust port area every 1 millimeter down. Right here is the compression ratio of the engine. If you don't know that, but you know the cranking pressure, you could enter that pressure right here, and it'll give you an estimated compression ratio. And that works unless your rings are pretty shot. Unless it's time for a ring replacement. This right here is millimeters above the port, which if you go to, let me see if I got it listed here. There's a website that I list. This one. You enter the stroke, the rod length, which if you don't know, just enter twice the distance of the stroke, and the height, which if you don't know the height, you can enter the duration and click calculate height. If you don't know the duration, you can enter the height and click duration. But the height is not from the top of the port to the TDC spot on the cylinder, but it's rather the opposite. So when you measure that, where is it? From here to the top of the cylinder, when you measure that, you're going to subtract that from the stroke to get the distance from the top of the port to BDC. And this next section we will do after we complete sheet 1. So we'll go back to sheet 1. The exhaust port, transfer port duration, the expected or desired end of the pipe power band, reed valve, Y for yes, N for no, carb diameter in millimeters. If you've taken a reading of the exhaust gas temperature, you'll enter here the millimeters from the piston face that the thermocouple is at, the RPM at which the temperature was measured, and the temperature that you measured. If you don't know that, just use this value right here at the end of the rest of these inputs here. You come back to it and enter that. So next would be the bore and the stroke. And here is a ideal header diameter, inner diameter. But usually people just use the existing diameter that they have, and so that would go right here. The inner diameter of the beginning of the diffuser, which would be larger if the header is flared. This right here is an ideal belly diameter based on 2.75 times the ideal header diameter. It's not to say that going over that is drastically terrible. It's not. Usually people enter as big a belly as they have space for. Right here is, well, let me see. Right here, let me show you. Oops. I don't know why that is not showing. Oh, here it is. This right here shows you the available inner pipe diameters that are common sizes. In this case, from Metals Depot online. So the program calculates an ideal header diameter and then selects one of these that's the closest, and it will put that value, that inner diameter, right here, and you can override it by entering your inner diameter. Let's say you make the stinger yourself. Okay, the header wall thickness, the thickness of the metal that the header is comprised of, and the wall thickness of the rest of the pipe metal. When I make a pipe, I make it with sheet metal of 0.7 or 1 millimeter thick. So stinger length is not critical at all. Just whatever suits your fancy. So then we can come back to the exhaust gas temperature, and it's recommending 623, so I'll just put 620, which is close enough. And on most bikes, a 140 or 180 millimeter long baffle will give you the best peak power. But if you've got a street or enduro bike or trail bike or trials bike, you would want a long baffle. So the baffle lengths are anything up to 300 millimeters long. So in this case I'm using 140. With that selected, we can go over here and just click this, and it will change these lengths so that these two numbers match, which is basically saying it's going to be very close to being able to give you this end of pipe power band RPM. And also, if you look at these secondary pipe wave charts, this orange zone right here, this is transfer closing, and this is exhaust closing. And this red zone right here is, which one is it? 2D. Let's second generation diffuser wave. It matches exhaust closing at the peak RPM. That's how the program selects the header length. And then the belly length is figured out according to the engine size and the baffle length entered here, and the diffuser just makes up the difference in order to keep these two numbers equal. Okay, after you're done with sheet 1, you will want to go back to sheet 4 and go to the transfer capacity calculator. This value right here is the total transfer widths, adding all of the widths together about 2/3 of the way down of the transfers. If you don't know that, it's not critical. This right here is a typical value for when it's got really generous porting, like in a racing engine. And this is like for more old style engines that have one main transfer on each side of the cylinder and a boost port. So whatever you enter goes right here, and then the millimeters above the transfer port. Like I said, you can use that website that I listed. Where is it? Yeah, this one. In the same way, and then just click calculate. And if the transfers are limited in any way for each of the RPMs listed here, it will show less than 1 being 100% capacity. So let's say if you've got an old style engine and you calculate, well, even in this case the RPM is low enough. It's more than adequate. Okay, and then you just go back to we've done that, then sheet 1, done that. Next would be sheet 2. Yep. So on sheet 2 we have the calculators for the diffuser and the baffle. And here you select automatic if you're going to let the program automatically engineer a 3-cone diffuser. And if you click automatic, you don't have to do anything else. It doesn't matter if numbers are entered here or over here. It does not matter. If you're going to do your own design, which is what I had to do on my Suzuki due to space limitations, you would on my Suzuki I made it a 2-cone, again because of space limitations, but I always recommend a 3-cone. So looking at sheet 1, we want 350 millimeters total. And oh, I forgot to do this, the belly, let me go ahead and set that equal to what is recommended. And I normally make a straight header, not flared. Okay. And that changes the temperature a little bit, but it's not critical. Okay, so 350 diffuser length. Let's see if I'm going to make the first cone 200 millimeters. This first section right here, cone calculation goes up to 180. So when you leave the next section 2 inputs blank, it becomes a continuation of the first section. So I'm going to do that. So if I'm going to make the first cone 300 millimeters long, the beginning diameter is 35 and the end diameter is actually it's unknown. Let me go back here. If I make a straight cone, end diameter is going to be the belly. What I said that was 120. Okay, straight would be 6.9 degrees. So with the 2 cone or 3 cone, the first cone is less. So I'm going to make the first cone like 4 degrees. So let me do that. What did I say? Make that. So if I make the first cone, I say 250 millimeters long. End diameter. So I'm going to fiddle with the end diameter until I get 4 degrees of the cone angle. I usually don't like to make the first cone any more than 4 degrees. Diameter 6.3, that's too big. So we'll make it 70. 4 degrees, okay. So I would enter 4 degrees right there. And because the second section is being used by the first cone, I'm going to use the third section for the second cone. So if the end diameter of the first cone is 70, the beginning diameter of the second cone is also 70. So we'll put 70 right here. And I don't know the angle, so I'm going to figure it out here. That's 100 for the second. Beginning diameter of 70. End diameter of the belly. That says it's 14 degrees. So I'd enter 14 right here. And then over here, I'm going to enter in all of these numbers. All these 18 numbers here, and if it's 250, that would be 7 more numbers here. And then, so then once I've got those 25 numbers entered here, then I would enter in these 10 numbers here in the gray shaded area. And when your header is longer than 360 millimeters, the continuation is right here. But I'm not going to do that because it's time consuming and I would bore you. So I'm just going to make it automatic. Okay, baffle, I said I'm going to use 140. So I don't have to touch anything other than click this right here. It says automatic single cone creation. I'm going to click 140, and you'll see right here the numbers have been entered in. If you do it manually, you just, same as the cone calculator, you use this to figure out what you want and enter the beginning diameters and the angles, and then the numbers in the gray zone go over here. Maximum of 30 for a 300 millimeter long baffle. So now we go to sheet 3, and this is actually the middle of the sheet. The very top of it is where it calculates the shape and height of the diffuser wave. The second section of that calculates for the baffle wave. And then right here we've got the return waves simulation in relation to transfer opening, bottom dead center, transfer close, and exhaust close. And below it is the pipe power calculator showing the intake value and the compression value. And those two are essentially multiplied by each other to come up with this. The idea being that you have to have both positive to get a significant value of pipe power. Even though beyond that and before that you have engine power, right? But this shows you the meat of the pipe power that is added onto the normal engine power. And then when you're all done, right here it shows you the lengths of each section. Right here is the inner diameters of each section, and right here is the angles of each section. And this right here is a gear RPM range calculator. If you don't enter a number right here, it'll use the same number you entered on sheet 1 as the end of pipe power band RPM. And on my site I tell you how to figure out what the ratios are between the crank and the rear wheel, which you would enter right here for each gear. And it'll show you over here the RPM range that is used in each gear. If you upshift at the same high RPM each time, this is how much RPM you use for each gear. This is useful if you want to get an idea of how much the pipe power band needs to span. Like if I'm using this on the street, I'm using all the gears. Second gear needs 1900 RPM. So I would want this to span at least that amount, probably a little bit more. So this is every 500 RPM. This is 1000, 2000, 3200. That's more than enough. But this is old. What you're going to do now is enter in the maximum horsepower, whether or not you know it or just guesstimate it, because this winds up being a ratio of that. And now that we've got all the numbers in sheet 4, sheet 1, sheet 2, all we got to do is click autograph, and it calculates the value of the pipe power band. And even though you asked for 10,000 RPM, it's usually going to be a little bit less, a little bit more, and you can adjust that by the header length. If you make it longer, you bring that more to the right. If you make it shorter, if you make it longer, you bring it more to the left. If you make it shorter, you bring it more to the right. And you can type in notes about the pipe, and right here this is the results of using a 140 millimeter long baffle. I recommend that you try each one of these baffle lengths and then see what the result is. And right here is an average power for every one of these RPM points, power points, that are over 1/4 of the peak of this. And this crazy computer, for some reason, is not showing the right numbers right here. If your computer does that, the numbers it should be showing are in this row right here. Oh, I think what it's doing is it's rounding off these numbers right here. I'm gonna unlock this sheet and go into that and try to get that to show exactly what is right here. This should be showing 6.1. This should show 5.6. So anyway, if you click on like store in row 2, it'll put the header length that you're using, the baffle length, the horsepower for these 5 RPM. Well, also this one also, but usually it's around 0. The average power that's listed right here, and the RPM range the range that those numbers that are above 1/4 of the peak cover. So I put 140 here on the second because I'm going to recalculate for 100 and put it right here, and 180, put it right here, 220 right here. So if I go back to sheet 2, I'm going to click 100. But now, because the valley length depends upon the baffle length, I'm going to recalculate these distances by clicking on this, which changes them a little bit. Now I'm going to go to sheet 3, recalculate the pipe power. Okay. I'm going to enter that into the first row. You can see we've got a boost in power, but a decrease in the RPM range, which is typical. Now we go to sheet 2, do the same for 180. Sheet 1, recalculate. You see 180's already been entered here for you. Recalculate. Go to sheet 3. Graph the power. And we're going to enter that in the third row. So you're going to be able to, in the end, look at these and decide on which baffle length you want to use on your bike. And when you're just starting and you want to clear that all out, you can click right here and it'll clear all those numbers out. And when you finally decided on your design, all the numbers that are on this spreadsheet will show up right here. And that's basically it. It's not that hard. Let me explain something about the calculation of the power. The compression value I get from the value of pressure at exhaust closing and a little bit before. Run through a special formula that has to do with its relation to actual PSI increase given the position of the piston and the exhaust port. And the intake value has to do with the average pressure up to transfer closing, the time span of this, and the value at transfer closing, because that has to be, it's optimally negative. And like I said before, when both of those values are more than 0, multiplying them times each other gives the pipe power. So that's about it. When you're doing this, you want to change any value. You go to sheet 1. If your exhaust duration doesn't really match the peak RPM that you're using, let's say on a bike that has a really radical exhaust port duration of, like, say 200, but you're only revving up to 10,000, that's kind of a mismatch, and what you're going to get is a dip right here in power, right in the middle. And if you're wondering about it, you can say, well, that dip happens at 8,500 RPM. So you want to look and see what's happening here at 8,500 RPM. You can type in that value here, and it'll show you. In this case, you've got a nice healthy diffuser wave that's still negative at transfer closing. You've gotten a really good pressure at exhaust closing, so the problem is not here. Then you would go to sheet 1 and look at the secondary waves graphs. And I've got other videos concerning that, but basically right here is this is time starting at exhaust port opening, and this is the end of the exhaust pulse. So that exhaust pulse is what's used to create the diffuser wave and the baffle wave. And if one of these secondary diffuser waves crosses this exhaust pulse right at the RPM that you have in question, in this case 8,500 RPM, if this green zone were crossing right over the center of the orange zone at 8,500 RPM, that would explain the dip, because that lowers the exhaust peak, which lowers the diffuser wave, and lowers the baffle wave, which lowers the pipe power. That's not an essential step, but I'm just helping those of you that are interested to understand more about what's happening when you're actually looking at the pipe power graph, if there's anything odd about it. If you want to look, well, let me mention this. This little green graph right here, you see it goes low right there, goes low right there, goes low right there. Those are the secondary waves. And this little dip right here is because of that. So this adds into the normal diffuser wave, and since it's going positive going, it causes this to be more positive going right here. And this causes a little bit of a dip right here. If you want to look at the waves without the secondary waves, enter in right there, and it'll show you what it would look like without them. When you get finished looking at it within, always put in Y for yes, because when you do the graphs, you want to be able to graph it with those secondary waves included. It will not put in Y for you automatically. Last but not least, I need to show what this little section on sheet 4 is. The pipe cone maker. If you've got a poster board or some large paper sheet, what you do is you enter the large diameter of one cone section here, the other end small diameter right here, and the angle from center right here, and it will show you right here the lengths involved. A plus B for this is 577 millimeters. This chord, this straight distance from one corner to the other, is 151. The angle right here is 15 degrees. So if you were to mark that with a ruler, what you would do is to 577 millimeters right here, you would place a mark. To 466 millimeters, you would place a mark. And then if you move the ruler, keeping the same pivot point a little bit farther out, you would do those two marks, move it out, do those two marks, and so you'd have a dotted line or dash line for these two, and then you can just fill it in freehand. It's not critical. The errors you're going to make when you use the 10 snips cutting the pipe metal are going to be more than the errors you make drawing this. So then when using the ruler, measuring for 151 millimeters from here to over here, you know, if you got that curve extended out here, you would just move it around till you find that where it crosses at 151. Make that mark and draw the line back to the pivot point. So then this section right here will be the pattern for your cone, which if you cut that out with scissors and you place that on top of the sheet metal, then you can outline it with a felt tip marker and then cut out the sheet metal. And then I made a simple video showing some of the basics of making a pipe that you can refer to, and there's other videos on YouTube on the subject. So that about does it. Thanks for watching.